Welcome to Calculus. Imagine you are managing a factory assembly line where two different machines are working together to build a product, and both are speeding up at different rates. Finding their combined acceleration after 10 complex stages by hand would be a massive, tangled mess of numbers. Today, we are going to learn Leibnitz's theorem, a magical mathematical shortcut that solves exactly this problem. It allows us to find the nth rate of change of two interacting things instantly, without calculating all the tedious steps in between. Now that we know what problem we are trying to solve, let us look at how this theorem approaches it. In formal calculus, Leibniz's theorem provides a formula for finding the nth derivative of the product of two functions. Suppose we have two functions, let us call them u and v, and both depend on a single variable x. We assume both can be differentiated at least n times without breaking down. The theorem states that the nth derivative of their product follows a specific expansion pattern. Interestingly, this pattern looks exactly like the binomial theorem from basic algebra, which you might remember using to expand expressions like a plus b squared. Instead of using powers, we use the order of the derivative. This concept leads us directly to the mathematical formula. Here is Leibniz's theorem. In this formula, the term on the left represents the nth derivative of the multiplied functions. On the right, the terms u sub n and v sub n represent the nth derivatives of the individual functions u and v. The symbol with n over a number is a binomial coefficient, telling us how many ways we can choose items from a group. Notice the beautiful pattern here. As you move from left to right across the formula, the derivative order of u decreases by 1 each time, while the derivative order of v increases by 1 each time. If you increase the value of n, the formula simply grows longer, adding more terms to the sequence. Before we move on, let us see this pattern with a concrete visual. What you are looking at is Pascal's triangle on the left, mapping directly to the coefficients of Leibniz's theorem on the right. The first row corresponds to the first derivative, the second row to the second derivative, and the third row to the third derivative. Notice how the numbers 1, 3, 3, 1 in the triangle perfectly match the constant multipliers in the expanded formula for the third derivative. This diagram shows us that we do not need to memorize complex coefficients. We can simply borrow the famous pattern from algebra to build our calculus equations. Now that we have our formula and visual intuition, let us apply to a real problem. We need to find the third derivative of the function x squared times e to the power of x. We must strategically assign our u and v functions. We pick v equals x squared because its derivatives will eventually become 0, which will eliminate many terms later on. We pick u equals e to the power of x because its derivative is always just itself. This strategic choice makes the math much easier. Since we are looking for the third derivative, we set our integer n to 3, meaning we will calculate 4 terms in total. Continuing with our setup, we now find the individual derivatives. We differentiate our v function 3 times. The first derivative is 2x, the second is 2, and the third is 0. Notice how the third derivative becomes 0, which is exactly why we chose x squared to be v. Next, we differentiate our u function. The exponential function is unique because its derivative is always itself. So every single derivative we need for u is simply e to the power of x. Finally, we write out Leibniz's theorem specifically for n equals 3, using the combinations from the third row of Pascal's triangle. Now we substitute all our calculated derivatives back into the expanded theorem. Every piece falls into its designated slot according to the formula. The first term combines the third derivative of u with the original v. The final term vanishes entirely because it is multiplied by 0. We simplify the expression by factoring out the common e to the power of x term, and we arrange the polynomial inside the parentheses from highest power to lowest. This gives us our final clean answer for the third derivative. Without the theorem, we would have had to use the product rule 3 separate times, creating a massive algebraic mess. Now that we have solved a specific third derivative, let us look at a more general case. We want a general formula for any derivative number n for the function x squared times sine of x. Again, we must strategically choose our u and v functions. We choose v equals x squared because its third derivative is 0, meaning our infinite series will actually stop after just 3 terms. We choose u equals sine of x because it has a predictable repeating pattern when differentiated. We find the first few derivatives of v, which are 2x and 2. Because all derivatives after the second one are 0, we only need to care about the first 3 terms of Leibniz theorem. Moving forward with this general case, we need the nth derivative of our u function. We use the standard formula for the nth derivative of the sine function. Every time you differentiate sine, it shifts the wave by 90 degrees. This shift is mathematically written as adding n times pi over 2 to the inside of the function. This general formula allows us to represent any level of derivative easily. Next, we write out the first 3 terms of Leibniz theorem. We replace the binomial combinations with their standard algebraic expansions, knowing that the rest of the terms are 0 because v sub 3 and all higher derivatives vanish. Now that we have all our pieces, we substitute our specific functions and their derivatives into the formula. It looks long and intimidating, but it is just a direct replacement of the symbols. We carefully place the sine terms and the polynomial terms exactly where the theorem dictates. Now, we just need to clean up the algebra. We simplify the fractions by cancelling out the 2 in the numerator and denominator of the last term. We also rearrange the terms so the polynomials are in front of the sine functions. This is the final general formula for the nth derivative. You can now plug in any number for n and instantly find that derivative. Now that we have successfully used this formula, let us understand where it comes from. We will prove this theorem using a logical method called mathematical induction. Mathematical induction is like knocking over a line of dominoes. First, we prove that the first domino falls over, which is our base case. For the first derivative, the formula gives us u sub 1 times v plus u times v sub 1. This is simply the standard product rule from basic calculus, so the base case is true. Next, we assume a random domino somewhere in the middle falls over. We assume the theorem holds true for some arbitrary positive integer m. This is our induction hypothesis. To prove the theorem, we must show that differentiating our assumed equation one more time gives the correct formula for the m plus 1 derivative. We differentiate both sides with respect to x. We apply the standard product rule to every single term on the right side. For the first term, the derivative becomes u sub m plus 1 times v plus u sub m times v sub 1. For the second term, we keep the constant coefficient and apply the product rule again. This expands our equation significantly, but it sets us up perfectly to group similar terms together in the next step. Continuing with our expanded equation, we group the terms that have the exact same derivative combinations. For example, we gather all the terms that contain u sub m times v sub 1. When we do this, we see that their coefficients add together. Here, we use a famous rule from algebra called Pascal's identity, which states that adding 2 adjacent combinations always equals the combination of the next row. Applying this identity simplifies our grouped coefficients perfectly. This final result is exactly the original formula, but with m plus 1 replacing n. Because it works for step 1 and working for step m guarantees it works for step m plus 1, the formula must be true for all positive integers. The proof is complete. So, we have proven that the theorem holds. This brings us to an important question. Why does this matter in the real world? In physics and engineering, we constantly deal with systems where two changing properties interact with each other. For example, imagine an alternating electrical current passing through a wire whose resistance is also changing because it is heating up. If an engineer needs to analyze the extreme stability of this system, they might need to calculate very high order derivatives to check for dangerous resonance or failure points. Without Leibnitz's theorem, calculating the fifth or sixth derivative of this complex product would take pages of error-prone algebra. This theorem allows computers and engineers to instantly write down the exact behavior of complex systems. Let us wrap up what we have learned today. Leibniz theorem is the ultimate shortcut for differentiating a product of two functions multiple times. By borrowing the famous coefficient pattern from algebra, it saves us from the nightmare of using the basic product rule over and over again. The secret to mastering this theorem is simply choosing your functions wisely. Always try to pick the function that eventually differentiates to 0 as your v function. This simple trick will make most of the long formula vanish, leaving you with a clean and easy answer. You now have a powerful new tool in your calculus toolkit. Great job following along.